Hi. So I work for Red Hat, and I maintain the Linux perf tools upstream in the kernel sources. And so the tools that I coordinate the development, I wrote lots of bits and pieces of perf, but lots of other people contributed, from hundreds of contributors over the years. It's almost 10 years that I've been doing this. So every time something new appears in the kernel, some new facilities, some new framework, some new way of doing things, you want to debug this thing, you want to profile this thing, and so you have to make changes to the profilers, debuggers, tracers, so that this new thing gets properly supported, and you can analyze performance and you can debug things in this new area. And the newest area, I would say, that's changing how a kernel implement things and new functionalities added, and how you do things that before required kernel changes or new modules or more difficult ways of achieving the same thing, is BPF. So in this presentation, I will try to show you briefly where it's being used, how it's being used, why is it so interesting, and as well try to talk about, show some of the tools that we can use to see it in action, to observe what kind of programs are running on your system besides the kernel and applications and libraries that everybody already knew. But then there's this new thing about BPF. So BPF is blossoming, is being used in lots of places because it provides flexibility, and it's one of the main reasons for you to want to use BPF, for people to use BPF, is to get better performance, and because you don't have to reboot the kernel, you don't have to load kernel modules to use it. It's being used for lots of innovation. I will be talking about some of this innovation that are connected to containers, to the cloud, to being able to continue to use the Linux kernel in hardware, networking hardware that is really faster than the pre-existing way of handling networking hardware was being done in the Linux kernel. So, but then you have to debug it, to inspect it, to audit it. People who are working on support have to be able to, when something doesn't work as expected, figure out what's happening. So what's BPF? The name is completely misleading. The only part of the name which is interesting is the F, which is filter. It has a lot of to do with filtering. Initially, it was Berkeley Packet Filter, was developed in Berkeley. It was presented in a Usenix paper in 1993. Throughout the presentation, there are going to be lots of links, and then if you want to know more about that specific part, you can get the presentation. It will be made available in the conference website, and I have it on the first slide. There was the link where all my presentations are stored. So the thing with this is filtering. So you have a TCP dump, which is a program for you to see what the packets that are passing through the network. You want to debug something. It's slow, what's happening, you want to see the packets flowing, but then you want to see just a subset of the packets that are flowing. You don't want to see all the packets because it will overwhelm you. There will be lots of packets that you are not interested. So you have to have a way to say, I want just the packets that are coming from or going to some specific host or some specific networks. And then you have a way to do that in the TCP dump command line. Previously, you would have to get all the packets and then do this matching. But this, it's very processor intensive. So you want to to tell the kernel that at the earliest possible moment, you will look at this instead of creating the packet, making it traverse all the way to user space, cross the user space, kernel space boundary. You get it at the earliest possible moment. Let's say when the driver gets this thing and passes it up one function, you look at this. If it matches what you want, then you put it into the ring buffer that later on will be processed by the TCP dump application. So the question is to reduce the volume of data that you copy. Recently, there was all this hardware problems that you meltdown and spectre and zombie load and all that made crossing from user space to kernel space more expensive. Syscalls in the Linux kernel were cheap, but now they are really expensive. So you don't want to cross this. We have to remember this when thinking about BPF. So the original BPF is just you get a bytecode, like an assembly language or an instruction set, very restricted one, where you get this expression from user space, like I want only the IP packets for the host 192 whatever, and transform this into a series of instructions, like, and then in the kernel, when the packet arrives, you will get this series of instructions, and it's going to say, oh, in the packet payload, you go to the header, and then at offset something where the port for the host is encoded in each packet. If it matches, then it goes on. So it's a way for you to pass a bytecode to the kernel, and the kernel will apply this bytecode at each packet that arrives in your machine. And if it matches, you pass. If not, you don't put it in the ring buffer, just process it normally. Then what is eBPF? That's what we are talking now. eBPF was just for packet filtering, old stuff. Extended BPF, it's what I described, but utilized in more context. You will not use just for packet handling. You will use it for tracing. You will use it for doing metrics. When you get to, let's say, when you get to allocate some disk block, you can attach a BPF in that place, and then we will talk about some of the facilities that are available. But you can get your code, call it, and it will look at the entry, which could be a packet, or could be a network, or a disk block, or could be a syscall, or could be lots of things. And it will do something with it. It has more registers than the original one, and the interesting thing is that it maps well to the instruction set of modern architectures like ARM64 and x86-64. It has a kernel verifier, because this thing gonna run in the kernel and with full privileges of running in kernel mode, ring 0. And so there is a kernel verifier that will look at this bytecode that you are passing through it, and you'll say, oh, this is safe. This is not accessing anything, any arbitrary memory. It's accessing only the stack that is associated with this, and it's using only a subset of functions that are allowed for using there, or using maps. We're going to see it in use, and this will become a little bit more clear. How does it look like? It's C language. Basically, it's a simple C program that we will attach to some place in the kernel, to a trace point or to a cape probes that you created in some arbitrary place, or that you put when any application does a syscall, like write or read or send a packet, or you can call this thing, and then it can do some stuff. It has maps, all sorts of maps The maps could be as simple as an array, or it could be a hash table, or it could be several other maps. I'll be talking about that. Then those maps can make you one BPF that's connected to, let's say, the packet receive can communicate can read and write a map, and another BPF that is when a buffer is passed to user space can access the same thing, and some tooling in user space like a monitor or a profiler can look at this map as well. So it's something that they can use and to coordinate work among this. And it can write to the perf ring buffer as well. And it can use this function bpf trace print k to insert messages to the ftrace, which is another facility in the Linux kernel. Restricted C, how does it look like? Let's say this is an example I have in perf, which shows that you have, just like C code, you include this bpf.h that's going to have these defines for probe, let's say. And what the BPF program is just from here to here. This is a very simple one. What this specific one does? It says insert a breakpoint in this function in the kernel, agr time and nanosleep, and then insert there. And when this function is called, you get the value that is in this variable rqtp tvsec, which is the number of seconds that is being passed to this nanosleep function. And then there is the first one is a context, which are registers, but it's not important right now. Then there is an error, a variable that this error can notify you that something went wrong. And then there is the second, that variable second, the parameter, which is this maps to this thing here. So what does it do? If any program in the system calls, asks the kernel to sleep for 5 seconds and something, then this variable will have this 5. And then here, if this variable sec is 5, it returns true. It returns true, which means don't filter this. Put it into the perf ring buffer. So this is, so in another terminal, I run perf trace -e, meaning I want this event. This is the name of the event. Then perf realizes that it's a file ending in .c and says, oh, this must be BPF. So it calls clang LLVM, and builds a object file, which is BPF bytecode, and inserts it into the kernel. It connects everything with perf, so that, and then in another terminal with this running, I say sleep 5. When I do sleep 5, it could be some other program in the system. I've just did this because it's easy to trigger, but I could have done this for, let's say, when a packet of 50 bytes, and then if some program in the system, Chrome or whatever, sends 50 bytes, I would get notified here. So I say sleep 5. It matches that thing, disappears on the screen. So if I would like to see when something happens in the system, I would write something like this, state the criteria for this to trigger, and would see it here. I could have asked it as well to have a backtrace, and then you would see the backtrace all the way to the sleep binary. So this is the simple one with C. You could do it like we would do with C in assembler as well. And this is actually, this is code from the systemd init system that everybody uses by now. Systemd, for DHCP, it has this, when it's binding to a raw socket as part of setting up DHCP, it wants to filter some stuff. And then it writes this as an array of instructions, and then here you put it into another struct, and then you use this to ask the kernel to associate with this socket, this program. Every time this socket gets something, this is run, and then packets that are DHCP passes, packets that are not related to DHCP are dropped. This is systemd. This is the first example of something using BPF already. So there are BPF program types. Each program type can do some stuff. Some program types will receive as its context what it operates on, a network packet, or it could be a... This one is interesting. We're going to talk about it later. For infrared programming of remote control, there are so many, and so they are using BPF now. We're going to get to that. Now, we have the maps as well. So the program can use maps to communicate with the other. So there are lots of maps, types of maps. So these are just a few, that there are 20 types more. Some of them are really simple, like array. You're going to do the lookup saying, I want the first argument, the first slot in the array, or the fifth or sixth or whatever. The other one is a hash. It's interesting when you have, let's say, a PID, or you have a string, and then you pass it, it will hash, and then you're going to get it like an associative array. You have stack, queue, a stack, a queue. There are several others. It's the documentation tells how to use it. Some of the functions that you can use in BPF to operate on those maps. Let's say you can do a lookup on an element. Like I said, for an array, you would say look up the first argument, the second argument. For a hash, you could pass a string, let's say the name of the file, or the PID, or the FD, or whatever. And you can do an update. You can say, oh, update this thing. And you can delete simple things in a key value store. So these are some of the BPF ID functions. Let's say you can ask, who is the user? That's right now. What's the PID and group ID for the current process? Well, what's the name of the short name for the current process? There are many others. This is for XDP. I'll describe a little bit XDP afterwards, but XDP is something that you do with BPF, which is Express Data Path. For processing packets really fast. That is something that's completely needed now for interfaces that are over 40 gigabits per second, 100 gigabits per second. Every nanosecond counts. Fault injection as well. You could put the probe in some place, and if you, let's say, you want to make any open that tries to open something in some directory, you say fail, and it stops, and you inject a failure. So, for instance, you could inject failure randomly just to try your software, to see if your software is handling when something goes wrong. Or you could use this to say, I want to run Chrome, but I don't want Chrome to be accessing anything in my directory full. This kind of thing, you can use this for a small BPF program to do something that before was kind of difficult to achieve. Infrared decoding, let's say. You have key down. I forgot to there's key press, key down and key in pause. And there is this URL which defines. The problem was you have the infrared receiver. The infrared receiver comes with a code, but this code, what's this code for? So everybody who lost a remote control, you have to get a generic one and then look at lots of tables. So those tables in the Linux kernel were being done via lots of kernel modules. Lots of kernel modules. The guy who is behind this said, no, I will use BPF for that. I will just do those things as BPF. So there is this BPF program type. You load it, and then when the infrared receiver gets a code, you transfer control to this, and this is BPF program is for Sony. The other one is for LG. The other one is for some other. So where it's being used? High-speed networking, tracing, in-kernel metrics, flexible filtering that you configure through maps, and again, the focus on decide early on, as soon as possible, to avoid processing costs. XDP, again, Express Data Path. You can use it for firewalling. You can use it for, in fact, the firewall in Linux, IP tables, has a lot of shortcomings and problems that, I mean, it show its age. It was good for 10 years ago, it was good 20 years ago, but now that we have the cloud and we have lots of containers, there are lots of problems with IP tables that make using XDP as part of this, and then getting the IP tables rules, the rule set that you have. People are working on something called BPF filter, like firewalling with BPF. So the user space is going to be just the same. You use IP tables, you have all those rules, and then when you call those things, the kernel will intercept this, and will transform that into a BPF program, and insert in the kernel. Then you're going to get in return the problems that you had with IP tables solved. And because the thing is, firewalling with this is when the packet gets into the network driver, before it creates the abstraction for a network packet, a socket buffer, a SKB, it just sets up DMA and etc., and then calls this XDP program. This XDP program is native x86 64 code. So it's very small, very optimized. So for writing firewalling, after this becomes widespread and problems are solved, we'll be basically writing C programs. You would not be using something like IP tables. You would just say that when a packet arrives, you're going to have a variable that it's the packet, the IP header, and then you say if the packet header is in whatever, in C, and then it's optimized for your specific rule set. It's not something that gets to a point and then you have to do lots of table lookups and stuff. It's just assembly. So there is this XDP redirect. I think that's really interesting. Here you have an image that shows a little bit how XDP works. You have the driver, you get here. It can, for instance, get a packet and then wait for the next one, and make a super packet, and then pass to the all-modified network stack that was already there. You can implement GRO as a BPF program. And then you can have the firewalling there. You say, oh, if this is for some, if it doesn't match some of the packet looks suspect for some reason or whatever, you drop it immediately, or you can forward to another thing. So it's kind of like a bypass, but it's not exactly a bypass. It's like a glue code. The kernel continues there, but you can put code that is validated. So it's not like, because people say, oh, you're running something inside the kernel, so it must be really secure. But when you load the kernel module, the kernel module can do everything, and it's running in ring 0 as well. This is something that was validated. Cilium is another case, which is for container networking. So you have lots of containers in the machine, and then the way they do is, one is responsible for something, they use TCP IP to communicate. So you have lots of get into the kernel, go up the stack, get to another container, go back the stack, and so you have to go on traversing the stack multiple times. With this, you can short circuit inside the kernel. So you get to the kernel, and just instead of traversing multiple times, you avoid these transitions to kernel user space. This URL here is gold. They have the best documentation about XDP and BPF available. Tracing, BPF as the observer. Again, tracing, if you want to trace, you can, lots of things happen inside the kernel. If you go to see all of them, you're going to be overwhelmed. It doesn't work. So there is this BPF trace, which is dtrace, the previous dtrace on steroids. That's way better. The guy who made dtrace popular was Brendan Gregg, who wrote a book, this book here. And he now is behind the BPF. So they say the thing that was missing in Linux is not missing anymore. It's way better than it was before in Solaris. This book is going to be out by November, I think. And all those names are new tools, very small tools that perform some specific thing that was difficult to do before. And then it shows in the block device or an IP layer or virtual memory or scheduler or system libraries for Ruby, Java. It's really fantastic. I mean, the problems that Linux had in terms of tracing are no more. Systemd uses it for several things. It uses a C group SKB type of program that every time that a packet goes to a socket that is inside some specific C group, your program will be going to be called. And when this program calls, sends a packet outside, your program is going to be called as well. And it uses this type of map, longest prefix match. That's what you use to try to see if a IP address, IPv6 or IPv4, matches. So systemd plus eBPF. You can do this, or I think on any machine in the Debian or wherever for quite a while already. And you see, if you do this, you're going to start a shell interpreter, and it will put BPF programs on the places that I described. If you do this, and then this is a systemctl status for that specific unit that we started, we'll show this extra line if you use that IP accounting. This extra line, IP 0 bytes in, 0 bytes out. And then if you send 2 ping packets, which are 84 bytes in length, and then you run that again, you're going to see that the IP now says that 168 bytes went in and 168 bytes are transmitted. Why? Because that's 2 times that thing. So it's using for IP accounting for a C group, which is really interesting because you can now see how many bytes are being transmitted by some specific workload that I have. So we're going to measure just that thing. If you want to block addresses, it's the same thing. If I use there and say 1111, you're going to see that 888 is not filtered, so it passes, but the one that I said should not be permitted is not being permitted. So that's a way for you to add functionality to the kernel without having to add code in the normal way. And if you commit a mistake in your BPF program and access something that you shouldn't, the verifier just say, no, it will not be loaded, and you tell you why, and then you're going to try to solve it. It uses a map. No, let me see. So how can I see that it was BPF? There is this tool, BPF tool prog, which is kind of like PS for you to see what the programs are running. And I knew that was the 2 last ones. So I say tail 6 because each one gets 3. So it says that it's a program of this type. They have a tag to identify it. It says the license is GPL. Says when it was loaded, by whom. That 176 bytes of bytecode and 127 bytes of JITed code. And says that he uses that specific map, 2893. And here I can see the maps that are in place while that thing is running. And it's that map. And I know that the key is 8 bytes, and the value is 8 bytes. So there's just one entry. I can do a map dump, and they're going to see that 1111 was the address that I say that should be blocked. And 20 is the length of this thing, which is 32 bits, an IPv4 address, which matches which should be there, which is the prefix length, 32, and the address, which is, and that value, number 2, that was the key. Number 2 is just some code that says block this or allow this to go. You can see with BPF prog dump the bytecode exilated, and I say tag, which was the second one, is A1B. And you can see how it looks like, what's the bytecode for BPF. So it's simple, it has some registers, whatever. At some point it says call this program, which will get the buffer from the packet and allow things. Here is going to be a lookup on that map where systemd said wishes the address that should be blocked. And here you have it, the JITed code, which is x86-64 code. Because one of the things interesting is that this thing here, this bytecode, runs on any architecture where a BPF is so I can run this on an Android machine with an ARM64 processor, or on my workstation with an x86, or on a access point with MIPS or whatever. It will validate this, it will look at this instruction and say, no, this is safe. I can go to the next step. The next step is transform this into JITed code, which in this case is x86-64. And that's for you to see how, more or less, what are the program types, how it gets loaded. Another example is Facebook Catran, which is a load balancer. They were using before IP virtual server, and now they use just BPF. So anybody that uses Facebook is using BPF all the time. All things that go to Facebook and get out of Facebook passes through Catran, and Catran is XCP plus BPF. There is a description for it here. And there are lots of other things, but in perf, you can. There are several ways, several changes that were made to the kernel so that perf can get the information about where a BPF program was loaded, how to obtain the source code, the bytecode, the JITed code. And then this is how the event is. Let me see. Let me go to show. It's a perf top, which is like if you run and there was those two BPF program loaded, sysenter, sysexit, were connected to the syscall entry and exit path. So you can see that it's just like any other function in the kernel. You can because it's normal machine code, just like the other programs. And with the changes that were before here, perf is able to it wasn't that address, so it's this program. And then you can as well, you can do perf report as well. This one was somebody investigating how to replace IP tables with XDP. So the driver in use was the Intel 40 gigabit network driver. There are some problems with, and then you can do perf annotate as well. You can show that program and say inside of that program what are the lines, what are the instructions that are taking more time. So I mean the experience that you have with BPF is the same one that you have with a normal program function in the kernel or outside the kernel. In this case, it's just that dump with bytecode that I showed before, but because this has extra information, just like you have with Dwarf, and you can intermix the original C source code with the bytecode, and you say, oh, this thing here in the source code generated this assembly, and we can map it back. Yeah, there are a lot of other things, a lot of other details, but I think that this is enough for you to have an idea of where it's being used, how it looks like, and should provide enough information for you to. There are lots of other slides in the presentation, but and pointers, and but this is becoming more and more used in lots of situations, firewalling, tracing, and all sorts of stuff. We have some 4 minutes for questions.
So can this be hooked up to functions from modules, and then can this be used for reverse engineering non-free kernel modules?
Not specifically BPF, but you could use perf for that. Yes, you could just like if or object dump to dump the. I mean, if the guy who provides you with a driver leaves debugging information, it's kind of non-proprietary because the source code will be there. I mean, the debugging information has lots of things. Among there is the original code. So if you are NVIDIA or some other proprietary driver provider, you would do strip, like remove the debugging information before you provide. If not, you can use it for, of course you can.
Can you hook it up to a function without a symbol?
Yes, yes. Because the thing is, it will always hook up to something without a symbol. The symbol is just a way for you to map to the address. If you don't have this mapping, but you suspect that that's where things are happening because you are doing profiling, let's say, and lots of things are happening there when you move the mouse or when you start some graphics intensive things, assuming that you are trying to reverse engineer a display driver. You say, oh, the action is happening there. It must be there. Let me dump the contents of that area and annotate it. Yeah, you can.
In case of systemd where you shown, do you have any metric that you can, I mean, why this can't be run every time? How much it will impact, just to see if it's enabled for some modules, how it will impact the performance, and why can't we have this on every time for some modules, for example?
I mean, I was even surprised that systemd was using it because I was using bpftool and then listing the programs in the system, and then there were some that I didn't know who was, and I investigated and realized it was systemd. I think that systemd did this just as a way as a first attempt of using this kind of functionality. For instance, I use BPF for tracing, for syscall tracing, because I have to get the pointer payloads, like the name of the file or the contents of struct, and it doesn't show up in the radar. It's really, I mean, as you see, the program is 100 bytes. It's a minimal number of instructions. I think that they could have left this enabled, but perhaps they did this in the past when BPF was not generally available, so it's kind of like a developer preview, something like that. In the future, probably they're going to have this enabled by default all the time.
How is it being used to inspect and debug live production systems, like big systems, big servers?
Yeah, but in the past, to see those, let's say, ftrace allows you to trace all the functions in the kernel, let's say, and it's enabled by default because the kernel community tries hard to have these with minimal impact when not enabled, and only have impact when you start enabling those things. So BPF is starting to get generally available in distribution. For Red Hat Enterprise Linux 7, or the latest one has part of this, just the part for, I think that for XDP, and not yet the tracing part. So we are passing through a transitioning period where people are enabling those things, and then with this BPF book, which will show people how to use this really easily, so people will want to have this. Using those things is like TCP live or BIO latency. That's just that. You don't enter and you get a top-like thing. Timeout.